Okay, so let us continue our discussion on Pauli flow. We have derived the Navier-Stokes equation for Pauli flow, assuming that the cross section can be arbitrary. So we have tried to find an expression for velocity as well as flow rate. Then we looked at the expression for the velocity and flow rate in case of flow between parallel plates. Now we go on and talk about flow in a elliptical channel. Okay, let us talk about flow in elliptical channel cross section. Okay. So, elliptical channel cross sections can be fabricated using silicon substrate if you use bulk micro machining, isotropic etching without agitation. Okay, then you would be able to fabricate elliptical channel cross sections. So, that is of practical importance. Okay. So, we can draw the cross section here. So, this is the elliptical channel. We can say this is y axis and this is z axis. The origin is at 0 0 and this is A and this point is B and this is the surface which you denote as del C and the cross sectional area is C. Okay, so we can write the equation of ellipse which is x square over a square plus in this case we are using y and z. So, y square over a square plus z square over b square equal to 1. So, the cross section del C becomes 1 minus y square, this is the boundary del C becomes 1 minus y square minus a square minus z square minus b square. So, for this case we can assume a trial solution. Okay, we can assume a trial solution and make sure that the boundary condition is satisfied, that means the velocity at the wall is 0. Okay. So, we can assume a trial solution u y z which is u 0 into 1 minus y square over a square, okay, 1 minus y square over a square minus z square over b square. So, this equation satisfies no slip. Okay, satisfies no slip boundary condition. Okay. So, now if you substitute this in the general equation, so the Navier-Stokes equation for Pauli flow that we derived. So, that was del square u over del y square plus del square u over del z square is equal to minus delta p over eta L. Okay. So, that is the general equation. Now, if you substitute this trial solution, okay, so this is the trial solution. If you substitute there, what you get is this, you get minus 2 u 0 into 1 over a square plus 1 over b square is equal to minus delta p over eta L. So, you can find u 0 to be delta p over 2 eta L into a square b square divided by a square plus b square. Okay. So, that is the expression for u 0 and that can be substituted in this equation to get the expression for the velocity field, okay, which satisfies the boundary conditions. So from there you can find the volume flow rate, the volume flow rate Q can be found. So Q will be equal to integration over the cross sectional area dy dz into u yz. Okay. Now if you substitute the expression for the velocity here, what you would get is Q will be equal to pi by 4 into 1 over eta L into AQ BQ divided by A square plus B square into delta P. So that would be the expression for the flow rate in a in an elliptical channel cross section. Okay. So now we move on to talk about channel of circular cross section, and as you know, circle is a special case of ellipse when the major axis and the minor axis are equal. Okay. So with that, let us talk about flow in circular cross section. Sections. So here we say that A equal to B, right. For the ellipse, if you write A equal to B, it becomes a circle. So this is a circle, this is let us say y, and this is z, and origin at 0 0. For A equal to B, if you substitute in this equation here, you can obtain the velocity field. So the velocity field u y z could be obtained as delta P over 4 eta L into A square minus y square minus z square. Okay. So basically what you do is you substitute A equal to B in this equation. So get an expression for u0 and then substitute here to get the velocity field. So that is what you would get. Okay. So this is nothing but the expression for the velocity field in case of flow through a circular cross section, okay, in Cartesian coordinate. Okay. So from here you can also find the flow rate. Flow rate Q will be equal to pi A4 divided by 8 eta L into delta P. So if you substitute A equal to B in this equation, this is what you would get. Okay. Now these two expressions can also be obtained by, this can be derived from first principle. Okay. So we can also do that. So for that we would consider a tube of circular cross section. Okay. So this is a circular tube. Let us say this is the radial direction, this is 0 and this is axial direction z, this is r equal to r equal to r. Okay. So this is nothing but this is called Hagen-Paiseli flow. Okay. Hagen-Paiseli flow. Hagen-Paiseli flow is a special case of the Paiseli flow where we are talking about flow in a circular channel cross section. Okay. So let us go back to our general equation, Navier-Stokes equation for the Paiseli flow case, Paiseli flow. So if you write in the same Cartesian coordinate, the equation in Cartesian coordinate del square u over del y square plus del square u over del z square equal to minus delta P over eta L. If you write in cylindrical coordinate, okay, if you write in cylindrical coordinate, it will look like this. Okay, del square u over del r square plus 1 over r del u over del r will be equal to minus delta p over eta l. Okay. So, now if you integrate twice, if you integrate this equation twice, what you get is this, you get u r will be equal to minus delta p over 4 eta l into r square plus C1 ln r plus C2. Okay. So, this is the equation that you get by integrating the above equation. Now, if you apply the boundary conditions, what are the boundary conditions? One boundary condition is that the velocity on the wall is 0, that is no slip boundary condition, and the other boundary condition is the symmetry boundary condition. Okay. So, the velocity gradient at the center vanishes. Okay. So, the first one is no slip, which says that u at r equal to r is 0, and the other one is symmetry. The symmetry boundary condition says del u over del r at r equal to 0 is equal to 0, right. So, these are two boundary conditions. Now, if you look at this equation and try to apply the second boundary condition, the symmetry boundary condition. So, you would see that this would require that C1 will be 0. Okay. Since you have a ln term here, if C1 is not 0, then it is not possible to obtain a solution. So, to obtain solution, the C1 needs to be 0. Okay. So, then you can apply the no slip boundary condition, this condition. If you apply that, you would get C2 to be delta p over 4 eta l into r square. So, you can write down the general expression for the velocity. So, u r would be delta p minus 4 eta l into r square minus r square. Okay. Right. So, while it was not very obvious to know the nature of the curve here, the velocity profile here, from the cylindrical coordinate you can see that this is parabolic. Okay. So, you can, the velocity profile is parabolic with the maximum velocity occurring at the center. Okay. So, this is a parabolic velocity profile. You can obtain the volume flow rate q would be 0 to 2 pi over the phi coordinate into 0 to r dr into u r. Okay. So, if you do that, you will get q equal to pi by 8 r4 divided by eta l into delta p. Okay. So, that is the expression for the flow rate in a circular channel cross section. Now, here we have made one assumption. Okay. In this equation we have made one assumption that u along theta is 0 and this is the angle phi, u along the azimuthal coordinate u phi is 0 and u of r equal to 0. Okay. So, this we have made, and this u is only a function of r and this is along z direction. Okay. Now, if we go back and we see the general solution that we obtained yesterday for a partially flow case, okay, for an arbitrary cross section, the expression we got was q equal to 1 over gamma delta p divided by 2 eta L into a cube over perimeter square. So, this is the general solution for Poiseuille flow that we obtained earlier, general solution for Poiseuille flow for arbitrary cross section. Okay. Now, if you apply this to a circular cross section, you would get exactly the same expression as here. Okay. So, if you apply to the circular cross section, then you would get q equal to pi by 8 r4 eta L into delta p. Okay. Right. So, the circular cross sections are also have practical relevance in microfluidics. It can be fabricated in silicon wafers. If you do bulk micromachining isotropic etching with solvent agitation, you would be able to produce circular channel cross sections. Okay. Actually, it is a semicircle that you will be able to produce, and if you bond two such semicircle channels, you will be able to generate circular channel cross sections. Now, another important point I want to discuss here: how do we define Reynolds number in case of Poiseuille flow, Hagen-Poiseuille flow, where we have flow through circular cross sections and the flow is driven by pressure force. Okay. So, in this case there is no characteristic velocity that is imposed onto the system, the pressure gradient is actually driving the flow. How do we define Reynolds number in this case? So, Reynolds number is typically defined as Reynolds number is defined as Re equal to rho u, let us say here the diameter will be 2r divided by eta. So, that is how you define Reynolds number. Now, here the average velocity is a function of the pressure gradient. Okay. So, average velocity u can be written as, if you know the flow rate, okay, we know flow rate here, and if we divide by the area of cross section, then we would get what would be the average velocity. So, average velocity will be q divided by pi r square. Okay. So, if you divide pi r square here, what you get is delta p over delta z. Okay. This is nothing but del p over L, okay, because pressure is varying linearly, and into r square and 8 eta. Okay. So, that is the expression for the average velocity. So, if you were to define Reynolds number for Poiseuille flow, the correct way to define would be rho into you will have RQ term appearing here, and delta p over delta z divided by 4 eta into you will have eta square, right. Flow in a triangular channel cross section. Triangular channel cross sections can be obtained again using microfluidic devices fabricated from silicon wafer. If you do anisotropic etching, you will be able to produce channel cross sections of triangular shape. Okay. Typically in anisotropic etching of a 1O wafer, you would get an angle between the inclined wall and the horizontal about 54.74. Okay. So, let us talk about flow in triangular channel cross section. So, unfortunately we do not have analytical solutions for flow through triangular cross section of any triangular shape, only for if it is if 3 sides are equal, okay, only if it is an equilateral triangle, then we will be able to derive an expression for the velocity. Okay. So, the analytical solution exists only for equilateral triangle. Okay. Let us draw an equilateral triangular cross section which would look like this. So, this is our y and this is z, this is a by 2 and this is minus a by 2, and the equation of this line is going to be z equal to square root of 3 y, and this line will be z equal to minus square root of 3 into y, and this line would be z equal to square root of 3 divided by 2 into a, and we have the origin here, and this is the boundary del C, and we are talking about this domain which is C. Okay. So, in that case we see that the triangle is bounded by 3 lines, okay, 3 lines here. So, the we can come up with so there are 3 planes that is forming the domain. One is z equal to square root of 3 by 2 a, okay, and the second one is z equal to minus square root of 3 into y and z equal to square root of 3 into y. So, these are 3 different planes that is forming this domain. Okay. So, we can write a trial solution similar to the elliptical cross section case. We can write a trial solution u y z equal to u0 divided by a cube into z, can say square root of 3 by 2 into a minus z into z minus square root of 3 y into z plus square root of 3 y. Okay. So, this is our trial solution. Okay. So, since we are multiplying 3 different planes here, we are dividing the a is the each side, okay, length of each side. So, a is length of each side of the triangle. So, if you substitute this trial solution in our partially flow equation. So, Navier-Stokes equation is del square u over del y square plus del square u over del z square is minus delta p over eta L. If you substitute in this equation, what you would get is this, you would get u 0 equal to 1 over 2 square root of 3 into delta p over eta L, okay, eta into L into A square. Okay. So, that is the expression for u0, which can be substituted in this equation to get the velocity field. So, from there you can find the flow rate q will be q is 2 into 0 to square root of 3 by 2 a dz 0 to 1 over square root of 3 dy into u yz. Okay. So, if you do that, you can get an expression for q which looks this square root of 3 over 320 into a4 divided by eta L into delta p. Okay. So, that is the expression for the flow rate through a triangular channel. Okay. So, next move on to talk about flow through a rectangular cross section. Flow through rectangular cross section is very important in microfluidic devices, is very widely used especially for polymer based microfluidic devices. The methods that the fabrication methods that we normally use leads to channels that are of rectangular cross section. Okay. So, now let us talk about flow in rectangular cross section. Okay. Unfortunately, in rectangular cross sections we do not have an exact solution. Okay. The best we obtain is a Fourier series expansion to approximate for the velocity profile. Okay. So, exact solution not possible here. Not possible. Best obtained is Fourier series expansion. Okay. So, let us look at a rectangular channel. Let us draw a rectangular channel here. So, this is let us say z and this is y, 0 is here, minus w by 2 plus w by 2 and the height is h. So, we are talking about a rectangular channel which has width w and height h, and we assume that the height h is smaller than w. Okay. This can always be attained in in a case where height is more than w, then it is possible to rotate the channel and obtain the height less than w. Okay. So, we say that w is greater than h. So, this is always possible to maintain. Okay. So, we again go to the Navier-Stokes equation for Poiseuille flow. Okay, which is del square u over del y square plus del square u over del z square equal to minus delta p over eta L. Okay. So, this we want to apply to this domain where minus w by 2 is less than y less than w by 2 and 0 is less than z less than h. Okay. So, this is the domain that we want to where we want to apply this equation. Okay. So, and here as you know, since it is parallel flow, u is a function of y and z only. Okay. and the boundary conditions, we can write down the boundary conditions u y z is going to be 0 for y equal to plus minus w by 2 and z equal to h. Okay. So, that is the boundary conditions. Now, we will take an approach where the term in that general equation for the Navier-Stokes equation for partially flow will try to express both sides in Fourier series, okay, and we will write Fourier series in the direction of z, okay, in the z direction, which is the shortest dimension of the channel. Okay. So, both sides of this equation, both sides of this equation is expanded as Fourier series along the third vertical z direction. And since we have to ensure no slip ensured, that means u y 0 equal to u y h equal to 0. So, the velocity is vanishing both at the bottom and top walls. You would ensure that by retaining terms proportional to sin n pi z over h. Okay. So, these terms are used where n is positive integer. Okay. So, now let us first do the Fourier series expansion for the right hand side. Okay. So, Fourier series for minus delta p over eta l. Okay. So, if you write minus delta p over eta l in Fourier series, you can write minus delta p over eta l will be minus delta p over eta l into 4 by pi summation n odd. So, only odd values of n used, infinity 1 over n into sin n pi z over h. Okay. So, this is how we can express the right hand side minus delta p over l in Fourier series. Okay. So, this summation term will yield pi by 4, which will get cancelled. So, you would have the same term minus delta p over eta l. Okay. So, now let us try to write the Fourier series expansion for the left hand side. Okay. So, Fourier expansion of u y z. Okay. So, we are not expanding the gradient term, but we are writing for the velocity field. Okay. So, the velocity field u y z can be written in Fourier series as this. So, n equal to 1 to infinity f n y and into sin n pi z over h. Okay. So, this is how we can write the velocity field in Fourier series. So, this is a the coefficient, this is a coefficient which is constant in z and a function of y. Okay. Now, if you substitute this and this in this equation, let us call it equation 1. Okay. So, what we would get is this, you would get del square u over del y square plus del square u over del z square. So, if you substitute this equation here on the left hand side, okay, on the left hand side, this is how it will expand. This will be equal to summation n equal to 1 infinity f n double dash y, okay, minus n square pi square over h square into f n y. Okay. So, just we are substituting this in the left hand side, this is what we would get into sin n pi z over h, right. So, let us call it equation 3, let us call this equation 2. So, now if you compare equation 3 and equation 1, okay, each and every term must be equal. Okay. So, for all values of n, for all n, the nth term in 1 and equation 3 must be equal. Okay. So, they must be equal. Now, and so what we see here, this is the we are comparing with sorry, let us call this equation 2, equation 3 and this to be equation 4. Now, this is the right hand side, okay, this is the right hand side, and that we are comparing with equation 4. So, we are in fact comparing equation 2 and 4. Okay. So, equation 2 is the Fourier series for delta p over eta L, and equation 4 is the expression, the velocity gradient, okay, viscous term. So, if here n is odd only. Okay. So, what we learn from there is f n y must be 0 if n is even. Okay. For any even, this term is 0, right. So, here only n is odd. So, in this equation, if n is even, since here we are not talking about odd or even, if n is even here, then the function must vanish. Okay. So, f n must be 0 if n is even, and if n is odd, then we can say that f n double dash y minus n square pi square over h square f n y will be equal to minus delta p over eta L into 4 by pi into 1 over n. Okay. And this is when n is odd. Okay. Now, if you want to solve this equation, this differential equation, it is a second order differential equation and it is an inhomogeneous equation, because the constant part is not 0. Okay. So, this is an inhomogeneous equation. to solve an inhomogeneous equation we need to divide the solution into both homogeneous as well as non-homogeneous solutions. Okay. So, we can write the solution f n y to be f n y inhomogeneous, let us say this is inhomogeneous, and f n y homogeneous. Okay. And this is also called the general solution, and this is particular solution. Okay. Now, to obtain the inhomogeneous solution, so f n y inhomogeneous, to obtain that one trial function, we can use a trial function f n y inhomogeneous to be constant, and if this is constant for the inhomogeneous solution, then this term will vanish. Okay, this gradient term will vanish. So, in that case we can find what is f n y. Okay. So, the function f n y for the inhomogeneous case would be 4 h square into delta p divided by pi cube eta L into n cube. So, eta must be differentiated from n. So, this is the inhomogeneous solution, and here n is odd. Okay. Now, to find the homogeneous solution or general solution, the right hand side must be made 0. Okay. So, for homogeneous solution we would have the equation f n double dash y minus n square pi square over h square into f n y will be equal to 0. So, we can write the solution f n y. So, this is inhomogeneous, this is inhomogeneous, and here we can write is homogeneous will be equal to a cos hyperbolic into n pi over h into y plus b sin hyperbolic into n pi over h into y. Okay. So, this will be the homogeneous solution. So, we can write the total solution here. Okay. So, you can write the total solution f n y will be equal to 4 h square into delta p divided by pi cube eta L n cube plus a cos hyperbolic n pi over h into y plus b sin hyperbolic n pi over h into y. So, if you substitute in our velocity equation, but before that let us try to apply the boundary condition. Our f n will vanish on the walls, plus minus w by 2 has to be 0. So, this is the boundary condition, mostly boundary condition. So, if you apply that boundary condition, f n can be written as f n y will be equal to 4 h square delta p divided by pi cube eta L n cube into 1 minus cos hyperbolic of n pi y over h divided by cos hyperbolic n pi w over 2 h. Okay. So, that is how we can write for f and y. Now, if you substitute this in our velocity profile, so u y z can be written as, so we have written how u y z can be written, okay, here. So, this can be written as 4 h square delta p divided by pi cube eta l into summation n is odd, right. This is what we have written here, n must be odd, right, because n for n even this is vanishing. So, only n is odd. So, n odd to infinity into 1 minus cos hyperbolic n pi y over h divided by cos hyperbolic n pi w over 2 h into sin n pi z over h. Okay. So, this is the expression for the velocity. Now, if you plot this here, if you plot here, okay, in this domain, what you would get is this. So, let us say this is our domain, this is z, this is y, what you get is this. Okay. So, here across this, since the walls are close to each other, the viscous effects make this velocity as parabolic. Okay. So, this is this is z direction and this is y and this is u at y equal to 0 and with z. Similarly, in this plane, if you try to draw the velocity profile, it will look like this. It will be parabolic around the edges, then it will look flat and then it will become parabolic. So, this is our this is our z direction, right, and this will be u of y h by 2. So, z will be at h by 2. So, this is h by 2. Okay. This is the middle plane, this becomes flat and is still parabolic around the edges. So, now we can derive an expression for the flow rate. So, you can write flow rate q will be equal to 2 into 0 to w by 2 dy to 0 to h dz into u yz, which will be written as this, q equal to h cube w delta p over 12 eta l into 1 minus summation n is odd infinity 1 over n 5 192 divided by pi 5 into h over w into tan hyperbolic n pi w over 2 h. Okay. So, that is the expression for the flow rate that we can calculate knowing the velocity field. Okay. Now, in the limit h by w tending to 0, okay, what you get? So, in that limit what you get is this term, okay, h by w tan h into n pi W over 2h would become h by W into tan hyperbolic of infinity, right. So, h by W is 0. So, the height is very small compared to the width. So, this term will become infinity, and so this term will become h over W. So, this is the case where the height is very small as compared to the width. So, in that case we can write q equal to h cube W divided by 12 eta L into 1 minus 0.63 h over W. Okay. So, this is in the limit where h is less than W. Now, surprisingly this simplified expression for the flow rate where the height is less than W is very accurate. Okay. When W is so this equation is accurate when h equal to W, the error is about 13%, and when h equal to W by 2, the error goes down to 0.2%. Okay. So, this simplified equation can be used to analyze flow in rectangular cross section when if h is little bit less than W, then also it will give you accurate results, and in the worst case when h equal to W, then also the error is about 13%. Okay. And if h is very small compared to W, in that limit it becomes like a flow between parallel plates. Okay. So, when h over W becomes 0, then flow between parallel plates. So, in this equation if you put this to be 0, what will happen? You get q to be equal to h cube W over 12 eta L. Okay. This is the solution we had seen earlier for flow between parallel plates. So, let us stop here today.